Assalamu alaikum and hello my dear students. In this video we are going to study Bernoulli's differential equation. This equation is special because it is not linear, but thanks to a clever substitution, we can transform it into a linear one, exactly like the ones we solved in the last video. First, let's look at the general form of a Bernoulli equation, which is y prime plus a of x times y equals b of x times y power of n. Notice that if n is 0 or 1, the equation is already linear. But if n is not equal to 0 or 1, the equation becomes nonlinear. So we are interested in cases where n is any other integers other than 0 or 1. To solve this, our goal is to linearize the equation. Step 1, we divide the equation by y power of n. We can write it like this. Then using the rules of power, we can write this. Now we introduce a new variable z. We set z equal to the term next to a of x, which is y power of 1 minus n. Next, we find the derivative of z with respect to x using the power rule. We can write it like this or like this. If you look back at our equation, we can see that the first term y prime times y power of minus n is right here. Then we can write it like this to simplify the substitution. So after substituting these into the equation, we get this equation. Here z instead of y power of 1 minus n, which is a linear equation that we now have to solve. As a reminder, we first need to find the homogeneous equation CH, then the particular solution CP. We sum them to write our general solution ZG. Then we back to our substitution to write our desired solution yg equals to z power of 1 over 1 minus n. Let's apply this to a concrete example. Let's take the equation 3y prime cosine of x minus y sine of x equals y power of 4. First, we divide everything by y power of 4 and we write it like this. Now we put this equal to z, that we can write also like this. It is easier to calculate the derivative of z, which is minus 3 y power of minus 4 times y prime, then minus 1 over 3 times z prime equals to y prime over y power of 4, which is this term. So substituting z and z prime back into our equation, it becomes much simpler like this. Our equation becomes like this, which is linear. First, we have to find the homogeneous solution of this equation. We will try to separate the variables and we can write it like this. Now we can separate the variables. We integrate the both sides. Then here we use the exponential to remove the logarithm and we can write the homogeneous solution like this. Now we have to find the particular solution by the variation of the variable c. We have to write it like this. To put this into our equation, we first need to calculate the derivative. I return to our linear equation, which is written here. We simply have to substitute zp and zp prime right here. Then I can write it like this. And zp equals to c times cosine of x. Sinus of x equals 1. Then we develop this to get cos squared x minus cx sinus x cos of x minus c. No, we have to multiply this by minus 1. So I continue. Now we can remove this and this. Then we isolate the derivative c prime. I need another page. Sorry. Then using the integration with respect to x, we get the tangent of x times minus 1. I return to our particular solution and we write minus tangent of x instead of c of x, which is minus sinus x over cosine of x times cosine of x. We can simplify it like this, and finally we get our particular solution in this form. Now we can write the general solution, which is the sum of the homogeneous solution and the particular solution. The particular solution is right here, and the homogeneous solution, it is here. It is a little bigger than this. Okay. Now we return to our original substitution, which is this. And now we can write y in function of z, which is 1 over the cube root of z. Then the general solution of our Bernoulli equation is the cube root of this. Okay. We finished with Bernoulli equation. So, to conclude, the secret to solving a Bernoulli equation is to transform it into a linear one by choosing the right substitution. Once you have the linear form, you simplify using the techniques we practiced before. So in the next video, we'll see how to solve Riccati's equations, where we will combine everything we learned so far. So see you in the next video, and bye.